So, we're doing a little bit of what we call trigonometric identities. There's a lot more you do with this in math analysis than we do here. But some of the basics, I mean, really even in math analysis, it's actually just the simpler ones that are most important. Most of the ones that we're going to use today. So the first is, what we mean by an identity is it's something that's true for all values of the variable or variables. It always has to be true. If it's not an identity, that means it's conditional. Most of the times when we're solving equations and we get like one value that's the solution, that's a conditional, because it's only true for one value of the variable. Right? So a silly example, if x plus 1 equals 5, then you solve it, x equals 4. That's conditional. The statement x plus 1 equals 5 is true conditionally, and the condition is x equals 4. Right? 2 times x plus 5 is 2x plus 10. I mean, we've got a property for that. That's called distributive property. That means that it's always true. Okay? So when you're simplifying and everything on the left ends up equaling everything on the right, that means that's not just conditionally true. It's true for all values of x. So what we're talking about today are trig equations that are always true. We need a little bit of these just to do the next lesson, which is going to be, okay, then let's solve trig equations. Because sometimes you've got to like invoke some kind of an identity to simplify, and then you'll be able to solve it. And maybe without that, you wouldn't see how to do that. So these are all the different trig identities. At least these are all the ones they have in our textbook, but we're not going to do them all. We're only going to go down as far as the Pythagorean identities. And Pythagorean identities, to me, are the ones that you really have to know, because they come up all the time. And they shouldn't be that hard, because, they're kind of based on Pythagorean theorem. If you understand a squared plus b squared equals c squared, then you should understand these identities. So I'm going to show these three, which we call them identities. To me, it's they're almost more like definitions than identities, especially the first two. Like the reciprocal identities just tell us that cosecant is the reciprocal of the sine, and secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. I think we kind of already knew that, but it's an identity. Right, there are three identities, reciprocal identities. The tangent and cotangent identities, tangent is sine divided by cosine, cotangent is cosine divided by sine. And that kind of makes sense with what we've already done on the unit circle, right? Sine is y, cosine is x, tangent is y divided by x. Okay. So, and then these are the Pythagorean identities. Sine squared plus cosine squared equals 1. And if you just remember that, I mean, you know, where does that come from anyways? Just think of the unit circle, right? If I have a unit circle and I have a triangle, right? This is the y, which we know is the sine. This is the x, which we know is the cosine, and we know that the radius of the circle is 1. So x squared plus y squared equals 1 is Pythagorean theorem, but that's sine squared plus cosine squared equals 1. So that's the identity. Now, if you can only remember that one, you can figure out the other two. Right? If I take first on this sine squared plus cosine squared equals 1, if I divide both sides, every term, by cosine squared, right, then this one on the left, that's sine squared over cosine squared, that's tan squared. The next term, cosine squared divided by itself, is 1. 1 divided by cosine squared is secant squared. So that's that first identity right there. And if I would have divided by sine squared, sine squared, sine squared, sine squared, I would have gotten the other one. I mean, there have been times when even I didn't remember, you know, like, what is it, 1 plus? I'm not sure, but I always remember sine squared plus cosine squared is 1, and that I can just figure it out for myself. Now, one note is, when you put the 2, like sine, and then the 2 exponent of 2, and then the theta, that's like saying sine theta in parentheses squared. That's the notation in trigonometry. If you want to square something, you put a little 2 in between those. If you want to cube it, you put a 3. You know, it just, etc. That's how you make an exponent on trig functions. Now, these three they're used a lot because every one of those could lead to a difference of squares factoring. Actually, I didn't do that right. I meant to show on this one the dividing by sine squared. I forgot I had that in there twice. Right, so there's the 1. There's cotangent squared, there's cosecant squared. That's this thing right there. Okay. But every one of these could lead to some difference of squares factoring. And, you know, a lot of these identities that we deal with, I mean, they are trying to make you use some of this kind of factoring that supposedly you've done before. I mean, it's almost like they're going out of their way to set things up where that's needed. So, for example, sine squared plus cosine squared equals 1. Well, what if I, for example, subtracted sine squared from both sides? Then I would have cosine squared equals 1 minus sine squared. And 1 minus sine squared, that's a difference of squares. That's 1 plus sine times 1 minus sine. Right, and the same thing here. If I, let's say I subtracted, in the sine squared plus cosine squared, I could have subtracted the cosine squared, right? And then I would have a different difference of squares. For this one here, I could, let's say, subtract 1, right? Tan squared theta equals secant squared theta minus 1. Okay, that'll be secant theta plus 1. Secant theta minus 1. I could have also subtracted tan squared. I could have made it 1 equals secant squared minus tan squared, right, which equals secant theta plus tan theta, and secant theta minus tan theta. And again, I could have done the same thing for this one too, right? I can subtract 1 or subtract cotangent squared. So you got to, a lot of the time when you're using these Pythagorean identities, it's by doing something like that, right? You're making a substitution because that's going to lead to a difference of squares factoring, and that'll make something cancel. And even in math analysis, I would say that, 50% of all the identities that you're working with, it all comes back to these right here. Okay. So, given that sine theta equals 4/5 and pi over 2 is less than theta is less than pi, find the values of the other 5 functions. Now, the whole point of this is we're in this section which is talking about the identities, and we just presented all these identities, so we're going to use these identities to do this. I mean, if it was me, I'd be drawing a triangle and doing it that way. But we're trying to show that you can use identities to do this. Right, we already know that the sine of theta equals 4/5. So which one of our identities is going to tell us the cosine of theta? If we know the sine? How about sine squared plus cosine squared equals 1, right? So let me keep in mind, so what quadrant are we in if we're in pi over 2 is less than theta is less than pi? Right. Unit circle, where is this? Quadrant 2. Right? Remember, if you got to think, pi over 2 is like 90 degrees, pi is like 180. In between 90 and 180 is quadrant 2. So if I use the sine squared plus cosine squared, right, then I'm going to solve, I'll just plug it in. So that's 4/5 squared plus cosine squared equals 1. So cosine squared equals 1 minus 4/5 squared is 16 over 25. Right? So I've got cosine squared equals 25 minus 16, which is 9 over 25. And what does that make the cosine equal? Take the square root of both sides. What's the square root of 9/25? 3/5, right? But it's actually plus or minus 3/5. It could be plus and it could be minus. Well, which is it going to be if you're in quadrant 2? The cosine is like the x-coordinate. Right? So if I'm in this quadrant right there, then the cosine's negative. So I've got to pick the minus 3/5, not the plus. So okay, now that I know the sine and the cosine, how can I find, well, the rest of them come pretty easily, right? For example, the secant should be 1 over the cosine, which is negative 5/3. The cosecant should be 1 over the sine, which is 5 over 4. The tangent should be the sine over the cosine, which is 4/5 divided by negative 3/5. Right? And the divide by 5s cancels, that's negative 4/3. And then the cotangent would be the flip, negative 3/4. Okay. So try this. I'm sure it's a you try next, right? So try to do the same thing for this one. Find if you're given the cosine of theta is 1/6, and you're in between 0 and pi over 2, find the other 5 functions. Okay, so cosine theta is 1/6. So we have to start at the same place. Sine squared plus cosine squared equals 1. So sine squared plus 1/6 squared equals 1. Sine squared equals 1 minus 1/36. So sine squared equals 36 minus 1 is 35 over 36. So sine equals the square root of that, which is the square root of 35 divided by 6. Okay, and from that we find the others. And let's see, the easiest one, we'll say the secant is 1 over the cosine is 6. The cosecant is 1 over the sine, which is 6 divided by the square root of 35. Rationalized denominator, 6 root 35 over 35. The cosecant. The tangent is the sine, the square root of 35 over 6, divided by 1 over 6. I didn't write that correctly. Which is the square root of 35. And then the cotangent should be the flip of that, which is 1 over the square root of 35, which is the square root of 35 over 35. Again, and which quadrant are we in? I should have said this before, but we're in quadrant 1, so everything was positive. So I didn't really have to worry down here when I took the square root. Yes, it's plus or minus when you do that, but we wanted the plus because you're in quadrant 1. But, I mean, I would have found it easier myself just to draw a triangle, right, in the first quadrant. So if cosine is 1/6, that makes that 1/6, and then use Pythagorean theorem to find this, and then do it from there. And you get the same thing. But the point of this section is, use the identities. Okay, try this one. Sine theta equals -3/7, and it looks like you're in quadrant 3. Okay, so what do we know about the value of the sine SIGN of the trig functions in quadrant 3? The sine and the cosine should both be negative, right? Because x and y are negative, which means the secant and the cosecant are going to be negative. But the tangent and the cotangent will be positive, right? You divide a negative by a negative, you get a positive. So when we go through this thing again, right, I'll write down sine squared plus cosine squared equals 1. Sine is -3/7, so -3 over 7 squared plus cosine squared equals 1. Okay, so cosine squared equals 1 minus, that should be 9 over 49. Cosine squared, 49 minus 9 makes 40 over 49. So the cosine is going to be the square root of 40 over 49. Well, let me show it like this. Plus or minus the square root of 40 over 49. Okay, now we know we don't want the positive. We need the negative. So definitely be the negative. And the square root of 40, you can simplify that a little bit, right? I mean, that's 4 times 10. So actually, it should look like 2 times the square root of 10 divided by 7. All right, that's the cosine of theta. And then we can do the others. Okay, so if we've got cosecant will be the easiest. That'll be the flip of the sine. Secant will be the flip of the cosine, which will be negative 7 over 2 times the square root of 10, which is negative 7 times the square root of 10 over 20, 2 times 10. No simplifying to do. The tangent will be the sine over the cosine, which will be negative 3/7 divided by 2 root 10, negative 2 times the square root of 10 divided by 7. And negatives cancel, divide by 7's cancel. 3 over 2 times the square root of 10 should be 3 times the square root of 10 divided by 2 times 10, which is 20. And the cotangent is the flip of that. So the flip of that, I'm just going to take these there. That'll give me negative, or give me 2 times the square root of 10 over 3. And we don't have to rationalize because square root's in the numerator. And we got all the signs right? Negative, 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 positive, positive. That's good. Check me for mistakes. I make them. Okay. Okay. So we move on beyond that kind of problem. It's a simplify. And you know when it just says simplify, you know, one of my favorite words, nebulous. It's kind of, you know, what are you supposed to do with that? How do you know how you're supposed to simplify? Well, you know, you're supposed to be thinking about those identities that you were just given to see whether there's something that leads to a simplification. If you see two different terms like that, one of them has got a denominator already, you got to be thinking, we're probably adding fractions here. And you might want to be thinking in terms of maybe you need to find a common denominator. Actually, for this one, I see the 1 over sine, but in the first term there's a cosecant. And doesn't cosecant equal 1 over sine? It does. So, in fact, I can rewrite this like this. Cotangent squared theta over the sine of theta. That's flipping the cosecant, plus 1 over the sine of theta. So I've got fractions, but they have the same denominator, so I can just add their numerators. Cotangent squared plus 1 divided by sine. Okay, and with practice, after you've been looking at these a lot of times, you should recognize cotangent squared plus 1. That was part of one of our identities in the Pythagorean identities. What does cotangent squared plus 1 equal? Right? That's cosecant squared. I'm going to go this way. That equals cosecant squared theta divided by sine theta. Right? That's Pythagorean identity. But how could we simplify that? Because aren't sine theta and cosecant theta related? Yeah, cosecant is 1 over sine. So, I mean, you could say, well, let's flip the cosecants down to be sine squared, but probably more likely you'd want to leave things in the numerator. So let's flip the sine to be cosecant. So that's cosecant to the third. That was a bad 2. To the third theta, right? Flip the sign. So that is a lot simpler than what we started with. That's the idea of simplifying. Try to find, we don't have many identities, and pick through those few and see whether there's something that leads to simplification. So try this one. See if you could figure out a way to simplify sine x times cotangent x times secant x. So did anybody come up with something? Anybody? Nick?
So cotan is cosine over sine, and then you multiply the sine to get rid of the denominator, so it's cosine times secant, and secant is 1 over cosine, so that.
Okay, so yeah, a lot of times, if you can't think of anything else to do, right, you can use the reciprocal identities and the tangent-cotangent identities to just turn everything into sines and cosines, right, and then see what cancels. Like Nick said, sine x times cosine x over sine x, that's the cotangent identity, times the secant of x, which is, let me put a multiply there, 1 over the cosine, right? So then sines cancel, cosines cancel, and the answer is 1. Okay, try this one. Again, I'd probably turn all these into sines and cosines to see what cancels. Did anybody do that? Get to simplify? Sarah? Did you do it? What did you get? 1? Another 1? These are getting boring. Sine x over cosine x times 1 over sine x. That's the numerator. The denominator is 1 over the cosine of x. Okay, in the numerator, the sine x's cancel. So you've got 1 over the cosine of x divided by 1 over the cosine of x, which is 1. I mean, it's secant x over secant x, but still. You might have said, well, I'm going to change this 1 over the cosine to secant, and then had secants canceling secants. I mean, it can happen when you're doing this stuff that, different people can choose slightly different ways to get to the same place, and that's fine, right? Makes it kind of hard to check, but, you check. I mean, in the end, as long as you apply identities in some logical way and get to the same place, you're good to go. Now, I think the next one is, verifying trig identities is where I don't like the simplify because, like I said, it's kind of nebulous. Where are we going here? You could end, two different people could simplify differently. The end result is actually something different, but maybe arguably more simple. So what are you going to say? But when you verify a trig identity, that's not true. There is going to be, there's more than one way to do it, but you do know that, what you're looking for. So to verify trig identity, again, identity means it's true for all values of the variable. It means that whatever's on one side of the equation must be equal to whatever on the other side. It won't look like that when you first start, but you will try to apply identities to one side or the other side or to both sides until you make them look the same. So you have a definite goal in mind here. So here's one. Verify that secant squared minus 1 divided by secant squared equals sine squared. You got to look and just try to think of what kind of identities do we have that are going to help me make the left side the same as the right side. I can think of two different things that I might do right away. Number one is, I think one of those Pythagorean identities I could like rearrange to have secant squared minus 1. Right? I could do it like this. I could say, I think it's 1 plus tan squared theta equals secant squared theta. So that means tan squared theta equals secant squared minus 1. So you could substitute for secant squared minus 1. Another thing you could do is you could take this, since there's two terms in the numerator but they got the same denominator, you could split it up and make it secant squared over secant squared minus 1 over secant squared. Right, there's another way to do it. It would look kind of different, but it would get to the same place. You know, how would that work? That would be secant squared over secant squared minus 1 over secant squared equals sine squared. Okay, this is 1 minus cosine squared equals sine squared. If I add cosine squared to both sides, I'm going to get sine squared plus cosine squared equals 1. Okay, there you go. That's an identity. So we showed that what we started with is true for all values. It's not a conditional. It's actually always true. Okay, again, if I would have done it the other way, right, I would have substituted here. I would have had tan squared divided by secant squared on the left. Tan squared is sine squared over cosine squared. And then in the denominator, we've got 1 over cosine squared. You know, the 1 over the cosine squareds cancel, and the whole thing equals sine squared. Right? That's if I use this identity right here. So there's more than one way to do these, but you got to think of, and again, Pythagorean identities are almost 50% of the time or more. That's what you're trying to find. That's what you're using. So let's try another one. Okay, got to make the left look like the right. And notice on the left, I've got more than one term. And both of those have denominators. So what I might want to do is, let's turn them into their denominators. Right, let's make this 1 over cosine plus sine over cosine which is 1 plus sine over the cosine. And we're trying to show that that's equal to cosine x over 1 minus sine of x. Okay. How do you think we could proceed from there? Yeah, I mean cross multiply. Notice that if you cross multiply 1 plus sine times 1 minus sine, that's the factoring of a difference of squares. So that's actually 1 minus sine squared. Right? And then if I cross multiply the cosine x times the cosine of x, I'm going to get cosine squared. So I've got all those same terms in that first Pythagorean identity are going to show up if I just cross multiply this thing. Right? So that'll be 1 plus sine times 1 minus sine equals cosine squared x, and that is 1 minus sine squared equals cosine squared x. And then by the Pythagorean identity, I know 1 minus sine squared is cosine squared. So cosine squared equals cosine squared. So we made the left look like the right. Verified. Check. So try to verify that one. Oops. What did I do? So there's kind of an obvious substitution to be making here. What was it? What does 1 minus sine squared equal? Cosine squared, right? If sine squared plus cosine squared equals 1, then 1 minus sine squared equals cosine squared. So you substitute it. Cosecant squared x times cosine squared. And cosecant is 1 over the sine, so that's cosine squared divided by sine squared. And that is, by definition, cotangent squared x. Same. So we verified. Okay, try this one. All right, you just turn it all into sines and cosines, and then you just cancel. Cosine cancels with cosine, sine cancels with sine. 1 equals 1. Check. Verified. And last slide. So what's the substitution for tan squared plus 1? Oh, come on. What is going on here? This happened once before. What was this secret? No. Escape. Okay. That's secant squared. Okay. What's the substitution for cosine squared? Minus 1. It's actually negative sine squared, right? If you start with sine squared x plus cosine squared x minus equals 1, then in order to have cosine squared minus 1, I would have to subtract the 1 to this side and subtract the sine squared to that side. That's how I get cosine squared x minus 1. So that's negative sine squared. So this one will be negative sine squared. I mean, you can see what you're aiming for over here, and there's clearly a negative in front of it. So, you got to be thinking, okay, it's probably that. Okay, so this one, take this together, that's 1 over cosine squared times negative sine squared, right? And there's your tangent. Negative sine squared over cosine squared is negative tan squared. Same. Okay. And that is it. And that is homework.